Complex numbers. So, 4 is all about complex numbers. And so far in your life, you've really worked with only real numbers. Okay? And the real number system looks like this. If you remember from chapter 1, we talked about number sets. We had real numbers. And inside of real numbers, we had irrational and rational. Inside of rational, integer, whole, natural.
Are we going to memorize those again?
You should already have them memorized, but you don't worry about it. Okay? Complex numbers. Okay? Here's what the complex number system is. Now, if I were you, I'd take a picture of this screen. Okay? So that you can understand what it takes to be a complex number. All it really is the real numbers and adding to that imaginary number. So the complex number system, we have real numbers and we have imaginary numbers. That's the only change. We've added imaginary numbers to the set of numbers that you already know. Okay? Now, today we're going to talk about imaginary numbers. Literally a figment of your imagination, because it doesn't exist as a real number. But we can use them just like they are real numbers. Okay? What is an imaginary number? I is the imaginary number. Okay. I is the imaginary number, and I is specifically equal to something. The reason why I wrote this over here is because this keyboard that I use here won't let me make a script R with the little curl, which is what you'll see most of the time in your book. Okay. Here's what it is. I equals the square root of -1. Now, keep in mind, when you take the square root of a number, what's underneath that square root, which is known as the radicand, we'll talk about radicals a lot more later on. What's under there has to be a positive number. Okay, because when I square something, whenever you square a number, you get a positive. And since squaring and square rooting are inverse relationships, typically what's under here has to be positive in order to be real. Well, what somebody figured out a long time ago is if we just make the square root of -1 some kind of number, then we can use it just like we would use radicals or other numbers as if they were real. And so that's what we're going to be doing with I. It allows us to still simplify and work and combine and things like that. Okay. Complex numbers can be written in this form, a plus bi. Okay, we call this complex number form, a plus bi, where a is a real number. So this is the real part over here because it doesn't have the I on it. This is the imaginary part. And that's all that says there. Every complex number, whether it's imaginary or real, can be written in this form. Now, when we write a number like 7, there's no imaginary part, right? We wouldn't put plus 0i. What's the point of that? We don't need to. But if I needed to write it in complex number form, that's what you would do. So all this time when you've been working with real numbers, you've also been working with complex numbers without really knowing it, because this part just wasn't really necessary. The same can be said with imaginary numbers. We can have 0 as the real part and just have an imaginary part. We usually don't write the 0 for the real part, though, and we'll talk about some of that stuff here in a second. At the same time, we could also say, let me give you another example. We could have something like this, 3 plus 2i. That would be an imaginary part. We could have a number just as like 4i. Could I put the 0 plus 4i? Sure, I could. Okay, but usually we don't because we don't need it. But if it asks for it in complex number form, you're just going to have to be able to shift between them. So here's an example. We'll say simplify the square root of -16. Now, here's the thing. Understand what we know about square roots. And I'll give you a different example over here. We know the square root of 25 equals what? How do we know that? Because 5 squared equals 25. Can you ever square a number and get a negative? No, you can't. Okay? And this is one of the things that drives me nuts about some of the things that you guys do on your tests and quizzes. Because you type it in your calculator and it comes out to be negative. Well, you didn't put the parentheses in. You can't ever square a number and get a negative in the real number system. Right? So this presents a problem. I can't square a number to get a negative 16. So this is where the imaginary numbers come into play. What you want to think is this. Okay, I can simplify the square root of 16. Right? We know what the square root of 16 is. Right? What is that? 4. Okay? And now we know what the square root of negative 1 is. So essentially this breaks down to, is this square root of 16 is 4? Well, what's the square root of negative 1? What? I. So what does this all equal? 4i. Okay. So what we've done is we've taken something that shouldn't make any sense to us, because I can't square a number to get a negative, and now I can simplify it down. The way I will say this, and you'll hear me say this a lot, is when you have a square root, we'll pull the I out. And by pulling the I out, what we've done is essentially pulling the negative out and turning it into an I, and then I can keep working on the rest of it. And that's what the imaginary number allows us to do. Okay? Questions on that? So far, yes. All right. Here's another one. Square root of negative 27. Okay, so right away, you should be thinking to yourself, pull the I out. Okay? Is 27 a perfect square? Can I take a number, square it, and get 27? No. Okay? So what we're going to want to do here is break 27 down. Is there a perfect square that is a factor of 27? That goes into 27? 9? Anything bigger than 9? Okay, 9 is the biggest perfect square that goes into 27. So what I can do is break it. Okay, so I can think of this as the square root of 9 times the square root of 3, because 9 times 3 is 27, times the square root of negative 1. Now I can simplify this, and I can simplify this. All right, because what's the square root of 9? Square root of negative 1? Okay, so this is 3 times the square root of 3i. Okay, now, typically when we write radicals together, what we do is take everything that's outside of the radical and put it in front, which goes opposite from the a plus bi form. And I'll explain why. Okay, so all of a sudden you're maybe wondering, why did I slide the I in front? And the reason is that sometimes what will happen is if you put it on the back, it can slip underneath the radical. So if you get sloppy, because if you get in a hurry, if I was to write this out, sometimes you'll do things like this, where you don't want the I under the radical. It's not supposed to be under the radical. Okay? So to avoid any sense of confusion at all, we just take it and put it in front, and then there's no doubt that that I is not under the radical. Now, there'll be times when they say, put it in a plus bi form, and this is not a plus bi form. So when you do it this way in a plus bi form, here's what it looks like. You got to have the 0 to be in a plus bi form, and notice how I sort of put some extra space in here, so that it's really clear that the radical ends and the I is outside of it. What I'm saying to you is, if you have to put it in a plus bi form, and a radical is involved in the imaginary part, just be sure that the I is clearly not underneath the radical. I don't want you to get that confused. Okay. Most of the time, however, this is going to be acceptable with the I in front of the radical. Okay?
That's the right answer. We just keep the radical.
Depending on what you do keep the radical, because that's as far as we can go. We're not going to plug the square root of 3 in our calculator and get some crazy decimal that never ends. We're just going to leave it like that. Yes? So the thing that we can do is we can take I and raise it to different powers. And when we do that, Here's to me where the really cool thing about imaginary numbers comes in. And I mean cool from a geeky math teacher perspective. I don't know. It just kind of is, right? I mean, in theory, if I square a number, or I square a square root, and they're inverse operations, they just kind of cancel each other out, right? In theory, what we're saying here is, this is the square root of negative 1 squared. Well, since squaring and square rooting are inverse operations, those things cancel each other out. So then what is I squared? Negative 1. So you're saying, okay, well, where's the cool part, Mr. Zukin? I took something imaginary, a figment of your imagination. It can't exist in real life. And when I squared it, it turned into something real, like magic. Okay? And this is the thing that somebody discovered at some point, that if we manipulate imaginary numbers in the right way, we can make them real numbers, just through algebra. Okay? One of the things you need to know is every time that you see I squared, you need to immediately change it to negative 1. Okay, that's one of those things you just have to know. I squared equals negative 1. Okay? And that's going to happen a lot. We're going to generate some numbers, and I'm going to turn i's into I squareds, and you'll see how that happens here in a bit. We have two other ones that we have to look at. We have to look at I to the third. Okay? And I'm going to give you 4 things here that you need to know. So I to the third is really I squared times I. Well, we already know what I squared is. It's just what? Negative 1. So what's negative 1 times I?
So it's just the same.
Negative I. Okay? I to the third is negative I. Negative I.
So how do you write that?
Just like that.
I know, but,
I to the third equals negative I.
oh,
Okay? So all I did here is I changed I squared to negative 1. Negative 1 times I is just negative I. Okay? And then the last one that we have to look at is I to the fourth. Okay? Well, I to the fourth is I squared times I squared. Well, what's I squared? So what's negative 1 times negative 1?
1.
Okay. So these are the 4 things you need to know. Okay? From this point forward, we don't write square root of negative 1. We just write I. We have to all understand and have an agreement and come to an understanding that square root of negative 1 just equals I, and we're going to write I. We're not going to write square root of negative 1. I squared is negative 1. I cubed is negative I. Oh, I got one more there. And I to the fourth equals 1. Okay? You need to know those 4. Now you can generate them like I did. It would be better to memorize them. I, negative 1, negative I, 1. And why this pattern is important is because you're going to be asked to find I to lots of weird powers. And I'm going to show you kind of a way to do that here in a second. So you're going to see problems like this. I know that's really hard to see. It says I to the 6th, I to the 35th. Put space in there like I did too. And I to the 81st. Because there's going to be some work in there, yes. Okay, I to the 6th, I to the 35th.
Can my calculator do this?
I don't know. I to the 81st. Okay. Now, here's 6, 35, 81. No. 6, 35, 81. Now, here's the key to this. Okay? What we're trying to figure out, the way that we simplify this is, it's going to be one of these answers. Okay? We're going to take it down to one of those answers. And the way that we do that is all about how many I to the fourths go into that. Because I to the fourth is 1, essentially what we're trying to do is drill this down so that I'm only left with one of these. And the way that we do that is essentially we do old-time division. We take the power and divide it by 4. Again, why the reason that 4 is important is because that's how many 1s go into it. So for this first case, what we're really doing is 6 divided by 4. Okay, old-timey division tells me that equals what?
Why are we doing that?
You're going to see in a second.
3 over 2.
1, thank you, say it again.
1 remainder 2.
1 remainder 2. That's what I meant by old-timey division. 1 remainder 2. Okay? 1 remainder 2. The remainder is the important part. Because there's 1 I to the 4th in this. And then there's an I squared left over. So why we've done that is I have I to the 4th times I squared. Well, we know what I squared is. That's what? Negative 1. And we know that I to the 4th is 1. So this is really 1 times negative 1, which is negative 1. Again, the key thing here is that it's all about the remainder. My actual answer is I squared, which is negative 1. We don't have to worry about the I to the 4th or how many I to the 4th go into it, because that's just 1. Okay? So now when I get down to something like this, I to the 35th, you divide that by 4, focus on the remainder.
It's negative I.
So why do we get 4 and 2?
It's negative.
It's always divide by 4 because we're trying to get rid of all the I to the 4ths that are in there. And because I to the 4th is 1.
And then why? What's the 2 from? Why do we use
That's the remainder. So look right here. Look right here. Okay?
What if it's a remainder
Okay.
of 5?
It can't be.
It's not possible.
Okay. So the remainder is either going to be 0, 1, 2, or 3. If you divide by 4, your remainder it goes in evenly. Remainder 1, remainder 2, remainder 3.
What if it's 8? Dude, it can't.
It can't
It's
be
4.
8.
8
It's
remainders.
divided.
All right. 35 divided by 4. How many times does it go in? 8. Remainder what?
3.
What this really means is that there's I to the 4th to the 8th. 1 to the 8th. Who cares? The point is it doesn't matter anymore. It's all about this I to the 3rd. That's going to be my answer. What's I to the 3rd? Negative I. Okay. So in reality, now I wrote it here just for your entertainment. But this is just 1 to the 8th. Sorry, I to the 4th is 1 to the 8th. Which means this is all just 1. So it doesn't really even come into play. Because 1 times anything is the same thing. All right? And this is actually I to the 32nd. And 32 plus 3 is 35. You don't need to write this. What you need to focus on is this, the remainder. Okay? And I to the 3rd is negative I. So on the next one, we're not going to worry about the first part. Okay? Because this part always confuses you. Just worry about the remainder. So do the last one on your own and we'll see what you got. Focus on the remainder. That's where you're going to find your answer. Okay? So how many times does 4 go into 81? How many left over? So the 1, the remainder. Okay? So my answer is I to the 1st, which is just I. So we just write I. Again, we made an agreement a little while ago that we don't write square root of negative 1 anymore. We just write I. Okay? So notice I didn't even put this part in here. Okay? I didn't even put the part in here this time because it doesn't matter. We don't need it. The remainder is what we need. And we raise I to whatever that power is. If it goes in evenly, and there's no remainder, what's anything to the 0 power? Do you know that? No. 1. Anything to the 0 power is 1. Or another way to look at that is I to the 4th. That's how it goes in evenly. Okay, so if you ever have that situation, that's what's going on there. Key thing here, again, key takeaway is when you divide this big power by 4, the remainder is the key number that you need.
So we don't need to worry about that 20.
Correct. Not at all. Just worry about the remainder and you'll get to your answer.
So we didn't even need to worry about the square root of the second verse.
That's what I'm saying.
So the remainder is just
No. There's so much more. Here we go. Let's keep moving. Next part. Okay, next part. Operations with complex numbers. We did finish. Yes, next, operations with complex numbers. So, just like with our real numbers, we can add, subtract, multiply, and divide complex numbers together. Adding, subtracting, and multiplying is not too bad at all. You know how to do it already, basically. You just haven't done it before with imaginary numbers. Division is a little more complicated, and I'm saving that one for last. What you're going to do with complex numbers is you're going to treat I like it's a variable, even though it's not a variable. But we're going to pretend that it is and use it like it is. And then we're just going to combine like terms, multiply, whatever, right? So, 3 problems. These are the same complex numbers. So here's one complex number, negative 2 plus 5i. I've used it all 3 times. The second complex number is 1 minus 7i. So this is an addition problem. I'm adding these 2 complex numbers together. This one is a subtraction problem. I'm subtracting this complex number from this one. And in the third one, we're just multiplying those 2 complex numbers together. Treat I like it's a variable and do everything that you already know how to do with this. Okay? Go. Keep this in mind. If you add complex numbers together, you should get a complex number, which means you'll have a term with an I in it. If you subtract complex numbers and you get a complex number, you're going to have a term with an I in it. If you multiply complex numbers together and you end up with a complex number, you're going to have an I in it.
Mr. Zugan, is this it?
So, yes, here's the thing. When you add, subtract, multiply, divide complex numbers, your answer can either be a real number or a complex number. A complex number only has an I term in it. There's no I squareds or i's to the third or anything like that. That's why we looked at those other things. Okay? So let's look at the first one. Okay? When I add these together, these parentheses are really only here to indicate this is a one complex number and to indicate this is one complex number. There's nothing in front being multiplied of either one of these sets of parentheses. So I don't have to distribute anything. And since it's plus, all I have to do is drop the parentheses. So I did that here. Okay, now you could have done that maybe in one step. And so now I'm combining like terms. Negative 2 plus 1, what's that? 5i minus 7i. Okay? Minus 1 minus 2i. How many got that? Okay, that's it. For that one, yeah. So I added these 2 complex numbers together and I got a complex number. Now, the second one, I'm subtracting. So the only difference here is that I have to distribute this negative, which makes this negative 1 plus 7i. How many did that? Okay, good. So now I have negative 2 and negative 1, which is what? Negative 3. 5i plus 7i. 12. So negative 3 plus 12i. How many have that? Good. Okay? Now, notice that both of these final answers are in a plus bi form, even though in this case it's a minus. Right? It's sort of like the b is negative 2. On this last one, yes, you have to FOIL, because it's this times this, and I have a binomial times a binomial. A complex number is a binomial, a plus bi. So when I FOIL, I should have gotten, on my first step, negative 2 plus 14i plus 5i minus 35i squared. And whenever you see an I squared, your first move is to do what? Make it negative 1. I can combine these, right? What's 14i plus 5i? 19i. So I have negative 2 plus 19i plus 35. So somebody asked me a little while, do you have to put it in a plus bi form? Does the bi have to come second? The answer is yes. So if you wrote 19i plus 33, your form is off. So what you want to do is put the real part first. So if I have negative 2 plus 35, which is what? 33, just put that in.
Why did the I squared go away?
Because I squared equals negative 1. Always.
And then you multiply those together.
You combine them together, yes. Okay? So, again, whenever you see I squared, Change it to -1, which is why this sign changes. And this concept here is going to be really important because we're about to talk about division. And division is much harder than addition, subtraction, and multiplication, but it involves multiplication, okay? And when we get to the next page and we start talking about division, you'll see what I mean. Are there any questions before we do that?
No.
Okay.
Yeah. We're just getting started.
So, this is division. Here's a problem that looks like division. This is -2i divided by 3 plus 5i. It's a fraction, okay? There's a couple rules. Because we know that I is the square root of -1. We understand that now. What this means is right now I have a radical in the denominator. And we're not allowed to have radicals in denominators. And so we have to do something called rationalize the denominator. And we're going to talk more about this in chapter 5 or 6. I can't remember. Okay. But for now, for complex numbers, you have to know that when you see an I in the denominator, we have to get rid of it. And the way that we get rid of it is we use what's called a complex conjugate. Okay, and all that a complex conjugate is this binomial, but instead of it being plus, we change it to minus. If it was minus, we change it to plus. So the terms, the numbers are the same, but the complex conjugate just changes the sign in the middle only. You only change the middle sign. Don't change anything else. Okay, so what would the complex conjugate of this be?
3 minus 5i.
No.
3 minus 5.
3 minus 5i. Only change the middle term. The 3 stays the same. We change the 5i to -5i basically. This doesn't change, okay? So what we have to do is we're going to multiply by 3 minus 5i. Again, this front term sign did not change. Only the middle sign changes. Okay?
Wait, is that just like a new one, or do we
So then
foil
is this
that?
gonna
No, we're going to end up foiling it, but hold on a sec.
Oh, jeez.
Now, if I multiply the bottom by 3 minus 5i, what else do I have to do? Multiply the top. Okay, because I can't just multiply the bottom, right? Because what is 3 minus 5i over 3 minus 5i?
1.
1. I'm really multiplying by 1. That's why we do what, when we multiply something on the bottom, we do the same to the top. The reason we do that is so that we're not changing the value. We're going to change what it looks like, but we're not going to change its value because we're multiplying by 1. Now, so yes, on top, we're going to distribute, and on bottom, we're going to FOIL, which is distribution. But here's what's important, and this ties back to what we did in factoring. Right? What does this look like an answer to? Kind of. Where the numbers are the same, but the sign in the middle is different.
Perfect squares.
Perfect squares, what did we call it when we were doing factoring? Difference of squares. So what would happen when we had a difference of squares is the middle terms would go away. They'd cancel out. And in this case, what that means is the middle terms that have the i's are going to go away. And we're going to turn this bottom into a real number. And that's why we use complex conjugates. Just as a point of reference, this is what should happen when I FOIL. Okay? When these numbers are the same and the signs in the middle are different, the middle terms drop out. So the O and the I cancel. And that's why we use complex conjugates, is to get rid of the middle terms. So that's what the strategy is. Okay? So what I want you to do is multiply the top out, see what you get. FOIL out the bottom, see what you get, and simplify it as far as you can. And that's how we do division. So go ahead and give that a shot and we'll see how you do. Here's the thing. All right, when I multiply across the top, I should get minus 6i plus 10i squared.
I squared is just negative.
Okay? And then on the bottom, I'm going to FOIL this out, and those middle two terms are supposed to cancel. Now, I wrote it all out for you. Hopefully you wrote it all out the first time too. Negative 6i plus 10i squared. The bottom, when you do the FOIL, 9 minus 15i plus 15i. That's good. We want those two terms to cancel. That's the whole point. If those two terms in the middle don't cancel, the O and the I don't cancel, the outer and the inner, outside, inside, whichever you wanted to call it, if they don't cancel, you did something wrong. Okay? A lot of times, people change this front sign, and that's wrong. Don't do that. Keep the numbers the same, just change the middle sign. And then the last term, minus 25i squared. Now, we already know that I squared is negative 1. Essentially all that does is it changes this sign and it changes this sign. So this is going to become minus and this is going to become plus. Which is good because on the bottom it's going to have a real number. Okay, so this becomes negative 6i minus 10 on top, 9 plus 25 on the bottom. So I have a real number now. I multiplied two imaginary numbers together and got a real number. So here's where I'm at so far. You're going to want to put these answers in a plus bi form. This is not a plus bi form. Okay, I need to have a real number part, and I need to have an imaginary number part. And here's how we separate when we have a fraction. Essentially what we do is we take the top and put it over the bottom, and we split the top up. So this first term, negative 6i, will go over 34. The second term, the minus 10, will go over 34, and that's how I can separate them into two fractions. So I'm going to put it in a plus bi form, and then I'm going to reduce it. The key thing here is the real part has to come first, which means this negative 10 has to come first. And I can just switch it because of commutative property. I can just switch it. So here I'm at. Negative 10 over 34, that's this part here, minus, since this is minus, 6 over 34. Now notice how I slid the I kind of to the side instead of leaving it up top, because it's supposed to be a plus bi. So this whole thing here, this is b. And then the I is sort of sitting next to it. So when we get a crappy fraction like this, which is going to happen, that's how you separate. Put both parts of the top over the denominator. Now I just have to reduce it. So how do I reduce negative 10 over 34? What goes into both of them?
5 does not go in the
What goes into both of them? 2. Okay, so if I divide them both by 2, I get negative 5 over 17. What goes into both 6 and 34? 2. So this is 3 over 17. Okay? That's my final answer. So like I told you, division is harder. There's a lot more steps. I don't know that it's harder. I shouldn't say that. There's more work.
So you can have fractions.
You absolutely can have fractions, sure. Just keep in mind, it all starts with the complex conjugate. Take the same binomial and change the middle sign, just like we did when we did difference of squares. We're factoring that way. It's the same idea.
So just give this to the.
The next thing that you have to do in your homework is you're going to solve using the square root property. Okay? And so whenever you have a quadratic, so far we've solved quadratics by graphing, and we've solved quadratics by factoring. We can also solve using what's called the square root property. And we use the square root property when there's an x squared, but there's no x term. This is when we use the square root property. There's no x term. So normally, we've said, make one side 0. Well, when we use the square root property, that's the time where we don't make one side 0. We put the x squared on one side, and we put the number on the other side. We separate them that way, and we're going to take the square root of both sides, essentially, is what we're going to do. Okay, so in this case, when I move 64, what does it become on the other side? Negative 64. So here's where I'm going to use the square root property. X squared equals negative 64. Right away, you're thinking, okay, I hope imaginary numbers are going to be involved, because you can't ever square a number and it equals a negative. Right? That's why this applies to what we're doing. All right? Now, whenever you take the square root of both sides, because that's what we're going to do here, to get rid of this squared, we have to take the square root. All right? Whenever you take the square root of both sides, there are two possible answers. Because let's think about an easy problem. Okay, if I had a problem like this, x squared equals 9. What's one value for x that will work? 3. Because if I take 3 and I square it, I get 9. What else could I get? Negative 3. So there's two possible answers. And like we've been talking about, since it's a quadratic and the highest power is 2, there's usually two answers. Okay, so the reason that when we take the square root of both sides, we have to keep in mind the plus and minus. Okay, so anytime I take the square root of both sides, and I'm going to write it up here. Take the square root of both sides, I have to squeeze in a plus or minus there. because there's two possible answers. Just like it was when we talked about x squared equals 9. It was 3 or negative 3. And in this case, when I take the square root of negative 64, there's going to be a positive answer and a negative answer. All right? So again, I take the square root of negative 64, pull the I out. What's the square root of 64? 8. So it's 8i. So my answers are plus or minus 8i. There are my two answers. One is positive 8i, and you can write it this way. If you want to write it like this instead, say x equals 8i and negative 8i. That's all that means. You can do that. But the plus or minus symbol just allows you to write the 8i once, and essentially means
It's essentially time.
Because it's